What do the Pony Express, Abraham Lincoln, rubbing balloons on your hair, an Italian called Alessandro Volta, and licking batteries all have in common? If you don't know, you probably should watch last episode before you venture any further because we covered a lot. But if we're all up to date, then we're going to jump from Volta and the first battery in Italy in 1800 to Denmark in 1820 to uncover the next step in the process that gave us the telegraph and brought to a sudden halt the heroic Pony Express riders. So now that we understand some of the basics of how electricity works, let's talk about a man named Hans Christian Ørsted and what he discovered. And with our newfound knowledge, let's see if we can begin to understand the process of how his discovery works. In 1820, Hans discovered that a magnetic needle could be moved by a wire carrying an electric current. Yes, I agree, that sounds a little bit underwhelming at first, but without this, there is no telegraph. So how does an electric current move a magnet? Well, we know that an electrical current is the movement of electrons in a conductor due to differing charges. So Hans could initiate a process where he created a negative charge at one end of a wire and a positive at the other, and an electric current would flow along the wire because of metal being a great conductor. But why would this electrical current move a magnetic needle? That's a great question, and the answer is fields. No, not those fields, we're talking about electric fields and magnetic fields. Let's start with electric fields first. Do you remember how we talked about how a negative charge is attracted to a positive charge, but two matching charges repel each other? That's because of what we call the electric field that surrounds any charged particle. And because they don't need to touch to influence each other, it's what we call a non-contact force. It is a force that will pull or push another particle that simply moves close enough to enter its field. And we know that push and pull is because of electrons wanting to make a move towards a positive charge or away from a matching negative charge. So that's the basic idea of an electric field. Now, let's jump to magnetic fields. We all know about magnets, right? They stick to your fridge and you can blow 3-year-olds' minds by moving metal with them. Have you ever noticed how if you have two magnets, if you flip them one way, they'll attract each other, but the other way, they'll push each other away? Well, we describe magnets as having north and south poles. The north pole of one magnet will be drawn to the south pole of another magnet, and vice versa. But matching north with north or south with south will lead to them pushing each other away. This is because each magnet generates a magnetic field. And when the right kind of metal or another magnet enters that field, non-contact forces will push or pull upon it. So far, this is sounding fairly similar to an electric field, right? A non-contact force that pushes or pulls when a corresponding field is nearby. But what creates this magnetic field? To explain this, we're going to have to go full Ant-Man and enter into the quantum realm to talk about atoms. Everything is made up of atoms, and within an atom you'll find protons, neutrons, and electrons. Protons have a positive charge, electrons a negative charge, and neutrons are neutral. If this sounds familiar, it's because we've been here before talking about electricity. And what we've discovered is that every proton and electron acts as a really, really small magnet. Why? We have no idea. But we also know that as those electrons whiz around the nucleus of the atom, they generate a magnetic field. And the direction that those electrons spin determines the nature of that magnetic field. And yes, we know that technically electrons don't actually spin in a circle, but it is a helpful way to illustrate what's happening. Now, in most atoms, the spin directions end up cancelling each other out, leveling out the atom's magnetic properties. But that is actually not the case in a few elements, and it's these elements that contain magnetic properties. And in some materials, when you get enough of those atoms together with all matching spin directions on one end, and enough atoms together with a matching reverse spin direction on the other end, you've just found yourself a magnet. Now we need to pause, because we just waltzed on by the most crucial piece of information there. Firstly, we found that charged particles create electric fields. Then, we learnt that when those electric fields interact with each other, they cause the movement of electrons, or electric current. And we've just learnt that it's the movement of electrons that also creates magnetic fields. So the behaviours of electrons are the source of both magnetic and electrical fields. So would it then be true that an electric current could also create a magnetic field that would interact with a magnet? Bingo. And this is what Hans Christian Ørsted discovered, which paved the way for the telegraph. When he sent an electrical current through a wire, it created a magnetic field that caused a magnet to move. And this discovery became codified as a process that others could now build upon. From there, the process of innovation began to accelerate. In 1825 in Britain, William Sturgeon invented the electromagnet, which significantly increased the magnetic force produced by an electric current. Further refinements were made in 1831 by Michael Faraday in Britain and Joseph Henry in the United States, and the door was opened for the creation of practical electromagnetic devices. Then through these inventions, 6 years later in 1837, the telegraph was invented. Twice. In Britain, Sir William Fothergill Cooke and Sir Charles Wheatstone gained a patent on a telegraph system that used 6 wires to control 5 needles on a receiver. And these needles, when receiving the correct current, would turn to point to a corresponding letter on the receiver's mounting plate. Meanwhile, at the same time in America, Samuel F.B. Morse was granted a patent for his own electromagnetic telegraph that used a new innovation he called Morse code. A code made of dots and dashes that corresponded with the letters and numbers of the alphabet. A stylus on the receiver end would rise and fall in response to the electronic signals it received, while a roll of paper was fed through, printing a code upon the paper that could then be translated to receive the message. Further refinements were made, and in 1843 Morse received funding from the US government to build a telegraph system between Washington DC and Baltimore, a distance of 60 kilometers. The first successful telegraph was sent on that system on May 24, 1844, with the message, "What hath God wrought?" From there, telegraph use exploded throughout America, while a similar spread happened in England in response to Cooke and Wheatstone's needle telegraph. And in 1861, almost exactly 1 year after the Pony Express's miraculous 7-day ride to deliver the news of Lincoln's election, the first transcontinental telegraph line was finished being built. Within days, the Pony Express, which had admittedly already been operating at a loss, went bankrupt and ceased operation, and the age of long-distance electronic communication had truly begun. Humanity was no longer tied to pen on paper and physical delivery. We had now developed a whole new language that could be transmitted invisibly through wires with lightning speed. And its advantages soon became very apparent as the Civil War began in earnest in America. By the war's end, the US Military Telegraph Corps had laid around 24,000 kilometers of telegraph lines throughout the country and had delivered an estimated 6.5 million messages. With each new process, from the voltaic cell all the way to Morse code 60 years later, the door was opened for innovations that birthed even more new processes. And this process, the telegraph, especially with the eventual use of undersea cables, opened up the whole world and in turn changed so much of how and what we could communicate. But as we know, the process did not stop there. This idea, the electric transmission of signals over distance, started the wheels turning on yet another process. And next episode, that's what we'll be exploring, as we continue our process of discovering the ongoing process of how we communicate.